I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on simple harmonic motion. In this video, we're going to talk about simple harmonic motion using simple harmonic oscillators or just oscillators. So, what is simple harmonic motion or periodic motion? Well, it's a motion that repeats itself over a period of time. The time for the repeated motion is the same for each oscillation as something moves back and forth. A couple of examples of simple harmonic oscillators are a mass attached to a spring. It oscillates back and forth, or a pendulum that just swings back and forth. These mechanical devices are known as oscillators or simple harmonic oscillators. So what causes simple harmonic motion as the box oscillates back and forth with no friction? Well, a restoring force. So what is the restoring force? Well, let's go through some vocabulary to understand restoring force. So the equilibrium position is where the spring is not stretched or compressed. So that's the point where the spring would be at its resting length, which means there's no force applied. Now, if we stretch that spring out to its maximum distance away from equilibrium, stretching it out, we have that spring force that is pulling back to the left. And we learned about this back in the energy unit when we did our Hooke's Law lab. So that means we have a force that's pulling this back towards the center. As it moves back towards the center, this force is going to be decreasing. But then as it moves towards the center, then the force decreases to zero, but then increases, it starts to compress and reaches a maximum value when it's compressed. And we have that force pushing back towards equilibrium. So the restoring force is always pulling back towards equilibrium, which is what causes simple harmonic motion. The spring supplies the restoring force in this case, and we know that Hooke's law governs that for springs. The spring force is equal to K times X. But in this case, X is constantly changing, which means if X is constantly changing, with the spring constant being a constant, that means the force is also constantly changing, which is important to note for what we're going to look at in the next several slides. So let's look at graphing a position time graph for the simple harmonic oscillator, the spring oscillator in this case. So if we define the equilibrium point as zero, and when we stretch that spring out to a maximum distance of x from zero, and then we can also oscillate it until it's compressed, and we're going to call that position negative x. So we have three specific positions that are marked. And what we're going to do is we're going to graph our position versus time graph. And as we graph, as this oscillator spring slides back and forth, we can start plotting points for when it reaches x, 0, and negative x. So we can see as time passes, we can plot those points for all the way through. Now, the question is, how are we going to connect these points? Well, we know that the spring force is changing, which means the acceleration is changing, which means the velocity is changing, which means the position is not going to be a linear change. So we know that it speeds up from x to 0, so that's going to be a curve, and it slows down from 0 to negative x and vice versa on the way back. So we're going to start connecting those with curves. So we can see as it oscillates, we have curves, and it ends after 2 full rotations, which is 2 cycles. So the graph that we have has a maximum value and a minimum value, or a negative of that maximum value. And that x max, or a negative x max, is just how far the spring is stretched or compressed. And that's known as the amplitude of the graph. That's a measurement from how far it is from 0. Now let's look at a velocity time graph using the same position. So when we stretch the spring out to its max, that's the point where it doesn't have a velocity because it's changing direction. Much like a ball being tossed in the air at the highest point, it doesn't have a velocity because it's changing direction. So that means at this point, we're going to plot a point for 0 on our velocity time graph. Then as it moves back towards equilibrium, that's the point where we have our maximum velocity. So the absolute value of the maximum velocity, but in this case, it's moving to the left. So that means we have a negative velocity. Then, as the oscillator then moves back towards negative x, well, at that point, the velocity is zero as well, because that's where it's changing directions again. So as the spring oscillates back and forth, we can sketch those points of zero and a maximum value as it oscillates back and forth. Now the question is, how are we going to connect these points? Well, as we stated, the force isn't constant, so the acceleration is not constant, which means the velocity is not going to be a linear function. So that we're going to connect these with a curve as well. So once we reach that positive x to 0, we know that that's going to be a curve. And continue to curve through each of these points until it reaches its full 2 cycles as it oscillates back and forth. And we can label those values Vmax and negative Vmax, or the maximum velocity minimum. And we know that that occurs when it passes through equilibrium. So each time it passes through equilibrium, it changes direction, which is why we have our curve as we do. So let's look at an acceleration versus time graph. So acceleration, as we reach the maximum stretch, we're going to look at terms of forces because we know that force is related to acceleration in Newton's second law. So that spring force is at a maximum value when it's pulling to the left, which is pulling in the negative direction. So we're going to plot an acceleration point in the negative. Then, as the spring oscillates and moves back towards equilibrium, we know that there is no force at this point because the spring's not stretched or compressed, which means that our acceleration value is going to be zero. Then, as the spring oscillates back and forth as it reaches that negative x position, we know that the spring force is now at a maximum pointing back to the positive direction, so we can plot a point there. And then as the spring oscillates back and forth, we can continue to plot those points as it reaches each of those positions. Now, again, because the force isn't constant, that means the acceleration is not constant and it's constantly changing. So acceleration is going to be constantly changing. So again, we're going to connect these dots with a curve as well, as you can see as we oscillate back and forth and finish those two oscillations. Now again, we're going to mark our graph with our maximum acceleration and negative maximum acceleration. And it's a note to note that at the maximum acceleration occurs when the spring reaches either the maximum stretch or compression, depending on which way the oscillator is moving. So what about a force versus time graph? Well, as this oscillates back and forth, we know that the force and acceleration are directly related in Newton's second law, so F equals ma. So the force graph is going to look very similar to the acceleration time graph. In fact, the only difference is the max and min values are going to be the forces, which is the acceleration times the mass of the object. So that maximum force equals the mass times the maximum acceleration, which is again governed by Hooke's law. How are we going to find those max values? So if we're deriving the maximum values for the kinematic graphs, first we're going to start with the position versus time graph to find the max and negative max value for the stretch or compressed. Well, we know that if we draw a line from x max all the way across, well, that's just how far the spring stretched or compressed for the negative, and that's the amplitude. So however far the spring stretched or compressed, that's the max or the negative max value. Now, if we look at a velocity time graph, if we're going to graph a velocity time graph, and we stretch the spring out to its maximum. That's our starting point, which the velocity is zero. What we're going to do is we're going to draw an energy bar chart, and we're going to go through this quickly so you can click the link above if you don't remember drawing energy bar charts. So the box and spring are our system, and as the initial situation, it's not moving. We know that we have all stored spring energy because the spring is stretched to its maximum. Then, as the spring oscillates and reaches equilibrium, the spring transferred its energy to the box. So we can draw our final position for the position of zero. And we know that if the spring transferred all of its energy to the box, that's going to be all kinetic energy. Now we could continue to graph this as it oscillates back and forth and find when it's at negative x. Well, that's just when the spring's compressed the most, so it transfers all the energy from the box back to the spring, which gives us stored spring energy. So what we're going to do is we're just going to look at position x and position 0, and we're going to derive our equation for the maximum velocity or the amplitude of our velocity time graph. So we know from our energy bar chart that the stored spring energy equals kinetic energy, and we can substitute the equations in. Then substitute the symbols for each. We have kx, mass of the block, and the maximum velocity. The 1/2s cancel out, and we solve this equation for Vmax. And we get an equation that Vmax is equal to the square root of kx squared over the mass of the block. Now we're going to simplify this equation. You'll see why in a later time, but we're just going to take the square root of x squared and bring that x out in front. So that Vmax is equal to x, or the amplitude, times the square root of k over m. And this is the max value on our velocity time graph. So now let's derive the maximum value for acceleration. So as this spring oscillator oscillates back and forth, we pause it at its maximum stretch and draw a free body diagram. We have the normal force and gravity balanced out, and that spring force, the restoring force, is at a maximum value when it's stretched. Now we can let that oscillator swing back and forth again. And once it reaches its negative x position, then we can see that the free body diagram is the same. It's just the spring force is pointing in the opposite direction. So it doesn't really matter which free body diagram we use because the spring force is the only force that's causing that acceleration. So we start with Newton's second law, F equals ma, and we know that that force is the spring force to provide that maximum acceleration. Well, we also learned that the spring force is k times x. So now we're set up, we can solve for our acceleration max value is kx divided by m. And we're going to write that x value out in front. And again, you'll see why. So a max is equal to x times k divided by m. Now here's a summary of those maximum values, or the amplitudes. We know that the amplitude of our position time graph is just how far the spring stretched or compressed. So x is equal to the amplitude of our spring oscillator. Using conservation of energy, stored spring energy equals kinetic energy, and we derived an equation for our maximum velocity on our velocity time graph. And note that that value occurs as the box passes through the equilibrium point either way. Now the acceleration time graph, we're going to use Newton's second law, set up the spring force to equal mass times acceleration, use Hooke's law for the spring force, kx, and then we derive our equation for our maximum acceleration, equaling x times k divided by m. And remember, this occurs when the spring is stretched or compressed the most. So this is an introduction to spring oscillators, simple harmonic motion. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.